In this video, we'll discuss the delete operation in a B tree. So in general, what we actually need to do is that we need to locate the value and then delete the value and restructure the tree. The second approach, similar to the insert operation, would have been that we could have simply performed one single pass. In the first approach, we need two passes. We first find the node, we delete the value, and then we restructure the tree in the second pass backward up. But in the second approach, what we can do that when we actually were searching the value, if we find a node that might delete or violate the properties of the B tree, we just adjust, restructure it there, and then we move downward. So that would have actually resulted in only one pass. But for this lecture, we would actually perform the two pass operation, and of course you can add the efficiency of performing only one pass in the implementation. But the idea would be very clear after discussing this operation of two passes. So let's start. In the delete operation in B tree, there are actually two cases. The first case is we are performing the delete operation from the leaf node. The value that we want to delete is in the leaf node. And the second case is that the value is in the non-leaf node. Okay. And if we actually understand the case one, we can simply handle the case two as well. Because remember, in the search tree, what we did was that when we perform the deletion from the non-leaf node, we simply moved that deletion to the leaf node, and then we handled the case of the leaf node. Similarly, in the B tree, we would again do the same. So we need to understand this leaf node case in detail. So what is there in the leaf node deletion is that there are further, we divided the discussion into two different points. The first point is case, we named it case 1A. And it's very simple that after the deletion of a value from the leaf node, if it still have adequate values in it, then we do not need to do anything, because there is no violation of the B tree property. So that's case 1A. We do not need to do anything. And then for the case 1B, what we need to do is that if the values after deletion are less than the minimum required number of keys in the node, then it violates the property of the B tree. So we need to do some restructuring and adjustment for case 1B. So let's see this case 1A from the tree that we grew in the previous lecture. If we want to delete H, we just need to search the value. It is smaller than M, we move to this node. The value is bigger than G, we move to this leaf node, and from this leaf node we found the value H here. We simply deleted this value from this node, and there is no violation of any property of the B tree, because this node still has 5 by 2, that is 3 minus 1, 2 keys. This, it still has 2 keys, which is actually not violating the property of B tree. So H is simply deleted from the leaf node, and no other operation is required. Okay. Now moving on to the case 1B. If we want to delete R from this tree, R is bigger than M, and R is between Q and W, so we move to this leaf node. So this is one pass. Now if we delete this node R, this value R from this node, it would have the only one key, that is S, remained in this node. So it actually violates the property of B tree. So let's take an analogy here. For example, if you are taking a quiz but you do not have a pen, what you would do is that you would simply ask your neighbor to borrow your to give you a pen. Okay. So for the first scenario, what you can do is that if you do not have the required thing, you ask from your right neighbor. If it has the required resource, in this scenario the pen, you would ask that to give you the pen. And if this particular person does not have an extra pen, then what you would do is that you would ask the other neighbor if he can give you the pen. If this person has the have an extra pen, has an extra pen, he would give you the pen. And the last case is if both these neighbor do not have the pen, then definitely you would ask your parent to give you the required pen for taking the test. So this is the entire discussion of case 1b. Okay, so this node is deficient of one key, so it would ask the right sibling. If it has an extra key, it would borrow this key. If this right sibling does not have the key, it would ask the left sibling. If it has the key, it would give the key. Otherwise, the node would have to ask the parent. So the nearest the scenario to resolve case 1b is are that we ask the right sibling or we ask the left sibling. If we do not find the value required value from both the siblings, then we would actually ask the parent node to give the to perform the readjustment. So in this case, when we delete r, this right sibling, it has an extra well key. It has three keys, whereas for order 5 BT, we need to have minimum two keys. So if it gives one key, if it gives one key to this node, then it would still be sufficient in the keys. So in this case scenario, we can take the value from the right sibling. Okay, so deleting R. Now this operation is not that simple. If we delete R and we ask this right sibling to give one value, it cannot simply give this x to this node because x is bigger than the value q or value w. Okay, so we cannot simply move this x into the deficient node. What we need to do, we need to perform one loop here. X would go and replace this w, and w would go in this node. So x would become the parent key, and then w can be its in the left node. So this deficient node now would have s and w in it, and this um node that gave the extra key would have y and z. Sorry, y and z in this node, and x would go into the parent. Okay, so that's the scenario for the deletion in the B2. Okay, so that's the final tree that we have for this specific scenario. So that x went up in the parent and w came down in the child node, and the node that gave the extra key, and now it has y and z. Okay, so that's the first scenario that the right sibling has an extra key. Now let's move on to the other scenarios as well. Okay, so for the left sibling, if we want to delete e from this node, so e is of borrowing something from the right sibling. So that you can understand. Now we'll discuss the scenario where the third scenario where both the siblings, if we delete e from this tree, both the siblings have the minimum number of keys and they cannot lend one key to this node. Okay, so in this case, we would ask the parent node to give one key to this node. Okay, but this is not very simple. What we would do is that on the other hand, if we borrow this g value from the parent, then we need to merge this um, g, k, and l value. Okay, so we will need to merge these four values in the in one node. And then of course this when we borrowed one value from this parent, it became the deficient node, so it need another value. So what it would do is that it would ask its right sibling. The right sibling does not have an extra value, so again it would ask the parent to give it the value. So this value m would go down, and it would merge with these, it would merge these two nodes. So in this case, the height of that tree is decreased. So let's delete this e from the tree. So the overall approach is that we create a new node, all the keys value from the deficient node. We actually merge a node, and in order to merge, we create a new node in which we have all the keys from the deficient node, all the values from its sibling. Okay, and then a key from the parent between the two combined siblings. So in this scenario, what we do here is that in this scenario uh, we actually borrow the value d from the parent. So when we borrow d from the parent, uh, see, when we borrow d from the parent, we merge this child and this child together. Okay, e is deleted, so d takes the value of position of e. So a c d f becomes one node, and g is the parent node. The g is the only value in the parent node. So now this node, after moving d downwards, this node is now deficient of one key. So it would ask the right sibling or the left sibling, which is not there, to give one value, but there is no extra key in either of the siblings. So it would ask the parent to merge the node. So m would come down, and the final node would be g m q x. That would be the root node, and the left of the root node would be this merged node. Okay, and between g and m would be this child, and then after m would be this child, after q would be this child, and after x would be this child. Okay, so this way we actually merge the children as well. Okay, so after this merging with the d, g is with the deficient keys. Then this g asks the parent to merge the node, and the final tree is something like this. Okay, so this is the entire case 1b. Okay, so we discussed that in case 1b, we can borrow from the right sibling, we can borrow from the left sibling, or we can borrow from the parent. And this borrowing from the parent may make the parent node deficient, and then if the parent node becomes deficient of keys, then it would again follow the same process upward. It would ask the right sibling, left sibling, or the parent, and in this way we can actually decrease the height of the b tree. Okay, so now we are left with the final case, that is the case 2. And in case 2, we remember that the value is deleted from an internal node. Okay, non-leaf node. So in this case, we simply do is that similarly as we did in the AVL tree, we can find the largest value in the left subtree or the smallest value in the right subtree. We would actually follow this one. We would find the smallest value in the right subtree, and we would move that value in place of the deleting value. Okay, and we actually moved by doing so, we actually moved the deletion to this leaf node, that was the position where the smallest value was present. Okay, so the deletion in the case 2, we actually move the deletion from the internal node to the leaf node by just finding the smallest value in the right subtree and moving it, replacing it with the value that needs to be deleted. Okay, so here in this scenario, uh, if we want to delete delete t from this tree, um, we simply found t here, which is a non-leaf node. What we do is that we move to the right subtree and find the smallest value. It could have been a tree. This is simply the leaf node, but if there are further levels, we would go to the left of this subtree. Okay, so in this specific scenario, w is the smallest value. So what we do is that we moved w here and replace this w with the t, and move this t on this place, and then perform the deletion here. Okay, so this deletion is in the leaf node, so it is the case 1. And then we handle this case similarly by either case 1a or case 1b. So that's the deletion in the internal node. So W comes here, and when we saw there, it was the case 1A, where no additional restructuring was required, and the node and the leaf node has the enough values in it. Okay, so that's the scenario of case 2. And for example, let's just continue with the and with another deletion. If you want to delete this node C, this value C. So we move to the right subtree and find the smallest value D. We moved this D here and move this C downwards and perform a deletion here. So upon this deletion, this node became deficient of one key. Now it has only one key, whereas for 3 or 4 or 5 we should have two keys. So it has only one key left. So what we do here is that um, we need to perform merging. So the right subtree, the right sibling, it does not have an extra key. The left sibling also not have an extra key. So what it does is that it asks the key from the parent. So parent would give this D again to this node and merge A, B, D, and E. Okay, and upon moving D downwards, this node would become deficient of one key. So it has only F left in the key. So what it would do is that it would actually ask the right sibling for a key. So this right sibling has an extra key, so this M would go up in the root, and this J would go down here. This J, sorry, J would go down here in the left subtree. Okay, so that's how we actually move this case B when there were less number of keys in the delete in the node that from where we deleted the value. So you see, after deleting C, this node E has less number of keys, so we borrowed the key from the parent. Now this parent is deficient of key, so we borrowed the key from the right sibling. So this is the final tree where the which actually fulfills all the properties of the B tree. So that's it for the B tree. Uh, if there are any questions, you can ask me. And remember, this is the last video lecture of this course. So um, hopefully now we'll see each other on the maybe on the demo of the project. So that's it for data structures course. Best of luck for the exams and the project, and uh, hopefully we'll see each other in some next course.